The first speaker is Professor Hachem Kadri. The title is Quantum Machine Learning, so please start.
Thank you, Yuka, for this introduction. Hi, everyone. I am Hachem Kadri from Aix-Marseille University, and I'm going to talk about quantum machine learning. First of all, I would like to thank you for this invitation and for organizing this nice workshop. So during this presentation, I will give you a brief introduction of the field of quantum machine learning. After that, I will choose two specific topics to show two different interactions between machine learning and quantum computing or quantum information. So please feel free to interrupt me if you have any question. So quantum machine learning is a relatively recent field of research at the intersection between machine learning and quantum computing. And the interest in this field is in the two directions. First, from quantum computing to machine learning, and in this case, in general, the goal is to design novel, more efficient, quantum-enhanced or quantum-inspired machine learning algorithm. But there is also an interest in studying the impact and the usefulness of classical machine learning to solve quantum information or quantum computing problems. Okay. And this is the other direction from ML to QC. So in my talk, I will give an illustration about different kind of interaction, but I cannot show all the results on this field. So I will choose only two interactions, and I will give more details on these two interactions. Okay. If you would like to know more about this field of research, maybe we can start by this review paper published in Nature in 2017. But you have to know that the field is evolving rapidly. So these are some rough statistics on related on the published papers on arXiv on quantum machine learning. So as you can see, the number of paper in 2022 is 5 times more than the number of paper in 2018. And the growth is still accelerating. One can also ask the question where the research of quantum machine learning is located. It is not easy to give a precise answer to this question because the field is relatively recent, but I took here a figure. I put the source in the slide, and this figure is showing the top 10 countries publishing papers on quantum computing and quantum communication. Why I took this figure? Because in general, research centers on quantum in these countries are conducting research on quantum machine learning. So in USA, in Canada, so Google, for example, has quantum artificial intelligence lab. In Asia, there are a lot of work on quantum machine learning from China, Japan, and India, and also many countries on Europe, especially United Kingdom, also Germany, France, and so on. Okay. The concept in quantum computing and quantum physics in general are very different from the concepts in the classical world. And this is, I took this figure also because it illustrates well the difference between these two worlds. And as you can see, there is like a border that separates these two worlds. So here, for example, you can see the cut of Schrödinger, which is simultaneously dead and alive. You can see here, for example, a line of smoke. In the classical world, you see only one line of smoke, but in the quantum world, this is maybe a superposition of two lines, and so on. So there are many concepts which are completely different, and which it is not always easy for people coming from classical machine learning to study and to try to solve problem in quantum machine learning. And in my work, in some sense, we are trying to create bridges between the two worlds, such that people from classical machine learning can go more easily and investigate a question on the quantum world, and vice versa. Okay. So this is the reason why we are organizing a workshop in September, and the workshop title is Bridges Between Machine Learning and Quantum Information. So the workshop is hybrid, and it is possible to attend in person, but also online. More information about the workshop can be found on the website of the workshop. Okay. Let me go now to the research on this field of quantum machine learning. It can be classified mainly into 4 categories, depending on the nature of the data, or the type of the data, or the type of the algorithm. So the data can be quantum or can be classical. The algorithm we will use also can be classical and can be also quantum. And depending on the interaction between the type of data and the type of algorithm, we can find an interaction and a subfield of research. We can say a subfield of research on quantum machine learning. It is true that most of the research in this field belong to the category CQ. CQ means classical data and quantum algorithm, because we have a lot of classical data, and there are many machine learning algorithm, classical machine learning algorithm, but this algorithm can be not necessarily efficient from a computational cost, or need a lot of data, and one can ask the question whether using quantum computation we can improve this algorithm. So most of the research are CQ. Let me give a simple example of kind of research in this field. So in general, we will try to use some already proposed quantum algorithm and adapt them for solving tasks on machine learning. For example, widely known quantum algorithm is the Grover's algorithm. It was proposed in 1996 by Grover. And the algorithm can find an element in a list of elements. So if we would like to solve this problem using a classical algorithm, and consider that your list of elements is not structured, we need an algorithm which has complexity linear with the number of items. So we have to check all the elements of the list to be sure if the element we would like to find is in the list or not. Grover proposed an algorithm which can do the same task, but with a complexity of square root of n. And this algorithm is based on the quantum superposition. Okay. I will give more details about this kind of work in the second part of my talk, because I will show you how to use Grover algorithm to solve a classification task and to design quantum perception algorithms. Okay. The second type of category of research is QC, and in this case we have quantum data and classical algorithm. Okay, so there are many problems in quantum information and quantum computing, and here the question is to see if we can address this problem using machine learning algorithm, already known machine learning algorithm. For example, one important task is quantum separability, also known by quantum entanglement detection. So quantum system can be separable or can be entangled. So entanglement is another features specific to the quantum world, like quantum superposition before. So having a quantum system and identifying if it is separable or entangled is a difficult task, is an important task. Okay. So some research can try to address this problem or approximate a solution for this problem using machine learning. This means that we can have a lot of quantum data or classical representation of quantum data, and after that we can learn a classifier such that we can find the decision function that separates separable states with entangled states. Another category is the fully quantum. In this case, we have quantum data and quantum algorithm. To illustrate an example, I took this work we did on quantum bandit. So bandit algorithms are well known in the field of reinforcement learning. And in this case, in general, we have a lot of slot machine, and the goal, for example, is to find what is the sequence of machine you should play such that we can maximize your gain. Okay? And in this case, we have a sequential problem, a sequential learning problem, and we have a dilemma between exploration and exploitation. So you will play the first slot machine. We will have a reward. The reward can be positive or negative, and depending on this result, we can decide to continue to work on this machine, or would like to explore other machine. This is why the dilemma is called exploitation, exploration. Okay? And so we try to revisit this problem using quantum concepts, and in this case we can have the quantum superposition, and this is why I took this figure. So as you can see, having this quantum superposition, we are able to play all the slot machine in the same time using the quantum superposition. In this case, the agent is quantum because it can be in superposition, but the reward we can obtain is also quantum. It can be on superposition. So the agent and environment both are quantum, and so we are in this situation where we have quantum data and quantum algorithm. Okay. It is important also to know that there are some research based on classical data and classical algorithm, which is also related to the field of quantum machine learning. This is seems a little bit weird in the first view, because we say that we have classical. What is the relation with quantum in this setting? Most of research in this case are based on quantum-inspired machine learning. So we will develop classical machine learning algorithm, but using concepts coming from the field of quantum computing or quantum information. And I will start by this part to give you more details about this category. So my talk will consist in two parts. The first part is CC, so classical data, classical algorithm. And second part is CQ, so classical data and quantum algorithm. I will not discuss about work on using quantum data, but after my presentation, we can have a discussion if you would like to know more details about this case. Okay, so to illustrate research on the class CC, I will talk about a work we did on partial trace regression and lower rank decomposition. This work was published at ICML 2020. Okay. The starting point of this work is trace regression. So trace regression is a linear regression model, which is the direct generalization of the standard linear regression model. As you can see, we have y is equal to trace b transpose time x. So y is the output data, so are scalars in this case. X are our input data, and b are the matrix of parameter. What is the main difference compared to the standard linear regression setting is that x now is a matrix. Okay? This is why the parameter b is also a matrix. There are some algorithm already proposed to solve the trace regression problem, and a class of algorithm are based on estimating the matrix B, adding a low-rank constraint on the matrix of parameters. So we have optimization problem similar to this one, where the first term, this is a standard square loss function, and after that here we have a regularization, and the regularization is on the singular value of the matrix. So norm 1 here is the nuclear norm, okay? And we would like to find the matrix B.
What is a star here?
Star, I would like to say that it is the true matrix of the model. So this is why I added start. Okay, so if you have a model, so B star is the true parameters of the model,
okay.
and we would like to estimate this true parameter. So when we solve this problem, we have here B hat, and we would like to find B hat near to B star. Okay. Any other question? Okay. There are also some work on trace regression based on removing the regularization, the standard, I would like to say, the standard regularization on the nuclear norm or our rankness, but adding a constraint. The constraint is that the matrix you would like to learn is positive semi-definite. So as you can see here, this is the minimization of the square loss function, but we have here B should be a positive semi-definite matrix, okay? And this can give us a PSD constrained estimation of the trace regression problem. This trace regression problem can be applied into in different contexts. For example, for the task of matrix completion. Also, another task in the field of senior processing is phase retrieval. Also, the problem phase retrieval can be written as a trace regression problem. In the quantum setting, quantum state tomography, where the goal is to estimate a density matrix. This means that the matrix, the PSD matrix with unit trace that represent our quantum system from a set of observable. And this also problem can be formulated as a trace regression problem. I will not enter into the details of how to write all this problem as trace regression, but as an illustration, I will talk quickly on matrix completion, which is widely known task in the field of machine learning. So matrix completion can be formulated as the following. So we have a matrix B, but in your matrix, let's say matrix B star, okay? And in your matrix B star, you have different points which are missing. To find this point, we can find an approximation by solving this kind of problem. So we have minimization. So P omega, this is a mask, such that we can take into account only the observed value of the matrix, and we can add here a constraint on the rank of the matrix. Having this strong rank constraint assumes that we have a strong relationship between the vectors of the line of the matrix, and this allows us to recover the missing points. So this problem, this optimization problem, can be written also as follows. So we have the same loss function, the same also constraint. Rank is equal or less or equal than R. R is an hyperparameter, and here we have the observed point of the matrix minus the trace the matrix we would like to estimate, and EIG. EIG is the matrix such that we have 1 at the position IG and 0 in the other positions. And so solving this problem, which is a trace regression problem, is equivalent to solving the matrix completion problem. Okay? All these results are already known. In this work, we proposed a new model, which we call it partial trace regression. To motivate this work, I took these examples. So the main difference in this model is that the output is also the outputs are also matrices. So the trace regression, the standard trace regression, we have the inputs are matrices, but the outputs are scalars. Now we are in the situation where both inputs and outputs are matrices. So to motivate this kind of situation, one can consider the problem of domain adaptation. So domain adaptation is in the case when target data are generated from a different probability distribution than the training data. So as you can see here, training data are the data in blue. And if we learn a classifier using the data in blue, we can find the separation like this. Since the target data are not generated from the same distribution, this solution could not be applied efficiently to solve the problem of target data. So this is the problem of domain adaptation, and there are many techniques such that one can adapt the domains to solve this problem. One possible solution is to generate some transformable examples. So here the idea is to generate new data such that we can mix the two domains. And after that, when we learn a classifier on the data considering the original data and the transformable data, we can learn a beta classifier. Okay? In many situations, data can be represented by positive semi-definite matrices. For example, in the field of EEG data, it is known that covariance matrices are a good representation of the data. And so in this case, each data we have is represented by a PSD matrix, a covariance matrix. To have a new transformable examples, we have to generate new data which have also the same properties. So this means that the new generated data should be also positive semi-definite. So we are in the situation where the input is a covariance matrix, and we would like to predict a new matrices which are also positive semi-definite. Okay. And partial trace regression model is designed to deal with this kind of situation. The idea, and after that the algorithm to solve this problem, are based on concept like partial trace. This is why it's called partial trace regression, but also on concept like completely positive map and Krauss decomposition. These concepts are widely known and widely studied in the field of quantum information. So this is why this kind of work can be considered as quantum-inspired machine learning methods. Okay. Let me now enter into the details. So some notation I will use. So MP to consider here matrices of dimension P by P. Also we have block matrices, and I use the notation MP parenthesis MQ. This means that we have a P by P matrix, but each element is a Q by Q matrix. So we will have a MQ times MQ matrix. This is a block matrix. Okay? And I will use this notation L, MP, and Q. This is to consider linear maps from the set of matrices of dimension P times P to the set of matrices of dimension Q by Q. Okay? So when we consider the trace of the matrix, so we will sum the values in the diagonal of the matrix. and we have a scalar. So this is adapted to trace regression, the regression problem, trace regression problem, because the output is a scalar. When we apply the trace to a block matrix, we will do the same thing, and we will output also a scalar. As you can see, in this case, the trace cannot take into account the block structure of the matrix. Okay, there is another notion which is called partial trace. So the partial trace is an operation that takes a block matrix as input and outputs a matrix. Here, for example, we have the block matrix, and after that, we will compute the trace of the first block, and this will give us the first element here of the matrix, and so on. So this block, this is the P time the block at the position P by P. We will compute the trace, and after that, this gives us this element. Okay, so partial trace taking input a matrix and outputs also a matrix, and this is why we use this to design a model suited to our situation where input and output data are matrices. Okay, so this is how our partial trace regression model is written. So y is equal to the partial trace of ax b, like before, so it's star, to mention that this is the true parameter of the model. Okay, and here, so x is a matrix of size p by p, a and b are the matrix parameters of size qm times p, and the partial trace is over the dimension m, which allows us to obtain after that a matrix as output of dimension q by q. Okay, if we take the particular case where q is equal to 1, we recover the standard trace regression model. And now, the question is how to learn, how to find the parameter of partial trace regression model. To present our methods, we need to introduce some concepts like the concept of positivity of linear maps. So, a linear map between matrices. So this is a mapping that transforms a matrix of size p by p to a matrix of size q by q. It is positive if it transforms a PSD matrix to another PSD matrix. Okay. There is also a notion a stronger notion of positivity, which is called M positivity, and in this case, a mapping phi is M positive if the mapping phi m is positive in some sense. So let me explain a little bit. So now phi m is a mapping that will apply to a block matrix. Okay, so phi, this mapping, the input is a matrix times p by p. Phi m, the input is a matrix of time mp times mp, a block matrix. We have this block matrix, and after that means that we apply the mapping phi for each block. Okay? If we apply the mapping phi for each block of the matrix and we obtain a positive matrix, in this case, the mapping phi is called mp positive. Okay? And there is also another more stronger notion of positivity, which is called completely positive. And a mapping phi is completely positive if it is m positive for any m greater than 1. Okay? Let me take an example to illustrate this. For example, first example is the transpose map. So the transposition is a map that transforms a matrix to another matrix. So the transpose of a PSD matrix is a PSD matrix. So the transpose is a positive map. But now, is it, for example, is it two positive map? No. This is a counterexample. So we have this matrix. Okay. After that, we will apply the transpose map on each block. So we apply the transpose here, we apply the transpose here, and so on. And we obtain this matrix by transposing each block independently. Okay. And this matrix have a negative eigenvalue. So this matrix is not positive. So the transpose map is a linear map which is positive, but it is not completely positive. It is not too positive. Okay. We can also have maps which are completely positive. This is an example. If we take any mapping phi written like this, so phi of A is equal to VA V transpose. So it is easy to see that when we apply here, for example, for a block matrix of dimension 2 by 2, it can be written like this. And so if this one is positive, the obtained matrix, it is also positive. And this map is is an example of a completely positive map. Okay, why we are interested in this notion of positivity? Because there is a theorem known in quantum information, the string spring theorem, which states that if we have mapping phi which can be written as follows, this is this trace, partial trace of AX A transpose. So as you can see, this is similar to our trace regression, partial trace regression model. Okay. If you have a mapping that can be written like this, if and only if it is completely positive. So if you consider this map, this means that this map is completely positive, and any completely positive map can be written like this. Okay, this is string spring theorem and allow us to have a connection between the partial trace regression and the notion of completely positiveness of linear map. But yeah, this is not necessarily useful from a computational point of view. This is why we go to a Krause composition, which is also another relation. And there is this theorem. In the field of mathematics, it's more known by the choice theorem. And in physics, more Krause decomposition. And the theorem states that if we have a linear mapping phi completely positive, then there exists a matrix AG such that the mapping phi X is equal to the sum AG times X AG transpose. And this is nice because if you would like to solve our partial trace regression problem, which based on the notion of a model based on the partial trace, we know that if we consider a model like this, that phi is completely positive, and if it is completely positive, that it can be written like this. And if we would like to estimate now the parameters, we have to estimate the parameter AG of this decomposition. This operator is also known as Krause operators in the Krause decomposition. Okay, so now our optimization problem for the partial trace regression is the following. We have a loss function here, L, and this is the output yi, and this is the mapping phi x. Since it is completely positive, it can be written as sum over g from 1 to r, ag, xi, ag transpose. And r is an hyperparameter and is called the Krause rank. Okay, and we minimize this over the matrices AG. Okay, maybe I will go fast here, but just to mention here that we can have a generalization bound without entering into the details. Maybe I can give you the main message of these results. So this is the true risk. So the risk computed on every data point generated by the probability distribution, but we don't know the probability distribution. In general, we minimize an empirical risk. So R at is the empirical risk, is this one. So it is computing over a fixed number. L is the number of data points, of fixed number of normal. This is what we do in practice. Okay, and here we have a control of the true risk. The true risk is less than the expected, the empirical risk plus this term. So if we reduce the empirical risk, maybe we can control the the true risk. And if we see here, we have the parameter R, which is the rank. And here, so the R plays the Krauss rank. It plays plays the role of trade-off between overfitting and underfitting. In the sense when R is too small, so the class of function in which we will search for a solution will be small, because the class of function is this one. So if R is small, so we have a smaller class of function. But in this case, we can have a better control of the true risk. Okay. But if we increase the complexity of our class, so R is high. In this case, we have a rich class of function in which we will look for a solution. However, so this term will be higher, and so the bound will be large. Okay, so the R is play the role of hyperparameters between. You have to control it to have a good trade-off between underfitting and overfitting. Okay. How this is related to the problem of matrix completion, as if you remember in the beginning, to motivate the trace regression problem, I talked about the completion, matrix completion. There is also a connection between partial trace and regression and completion. And this is given by the following result. So phi is a completely positive map if the block matrix constructed by applying phi to EIG, this is the matrix having 1 at the position IG and 0 otherwise, is positive. Okay, MIG is positive. Okay, this is interesting. I will show in some experience, because in some sense this allows us to complete matrices with incomplete information, but in the situation where we don't have only scalar are missing, but when we have blocks are missing, because here the output of phi is a matrix, so we can complete not a scalar, we can complete a block. And in the field of matrix completion, it is difficult in the situation where we have localized missing point. It's more difficult to complete the matrix than the situation where we have a dispersed missing point. Okay, let me show you some experiments quickly. Yeah, here are some experiments with different comparison, and this is in the situation where we have a matrix to matrix regression problem. We consider the situation where the input is a PSD matrix and the output should be a PSD matrix. One advantage of our method is that the output will be automatically a PSD matrix. So this is guaranteed by our method. Okay, this is some results we obtained. Let me go to the completion, matrix completion simulation. So this is the original matrix. After that, we removed blocks. Now, so in general, we remove points. Here, we removed blocks. So we are different blocks here, which are missing. And after that, we apply the partial trace regression problem. As you have seen, so when we apply this, the output of the model is a matrix. So in this case, the output is a block. So after that, we will use the cross decomposition. We will find the Krauss operator, the parameters of the matrix, and we apply phi to the matrix EIG to complete the blocks. And we obtain then this kind of results with some good results. Okay. After that, we try it also in the situation, the standard situation of matrix completion when we have different points which are missing. It works as well. We tried a more difficult situation when we have a lot of missing points. So this is the number of missing points, and applied our approach. We obtained this result, which is not very good. But we tried, like in deep learning setting, drawing a second layers of Krauss decomposition. So We have a first layer about cross-decomposition and a second layer of cross-decomposition, and also we added some nonlinearity. This is why here is called reconstructed matrix depth 2. This is 2 layers, and we obtained good results here. But this is really experimental. All the theory already shown are not valid in this situation, because we have not a linear map, we have a non-linear transformation, and so on. But at least we observed that experimentally we can improve the result. So I have to go to the second part, but you can look at the paper to see more details and more comparison about partial trace regression model with other regression model. Okay. My second part is about the class CQ. And here, I will talk about the work we did on quantum perception, and one specificity maybe of this work compared to other work is here we would like to see the advantage we can obtain when using a quantum algorithm from computational point of view, but also the statistical point of view. In the beginning, most of the research of quantum machine learning, when using a quantum algorithm, people are trying to have algorithms such that the running time is better than the running time when using a classical algorithm. But for machine learners, there is also another important question related to generalization. So the goal is not only to improve the computational complexity, but also to see if we can have any gain from a statistical point of view. And this is the main focus in this work. So we will like to show this trade-off between computational improvement and better statistical guarantee in the case of quantum perception. Okay, I need to introduce some basic concepts of quantum computing. So the main difference is now we don't have bit, but we have qubit, so quantum bit. So bit can take 2 values, 0 or 1. In quantum computing, we have this quantum superposition. In this sense, quantum superposition means that a qubit can be at the same time in the position in the bit 0 and the qubit 0 and the qubit 1. How we formulate this mathematically? So in general, we consider a qubit, one qubit is a vector in C2, okay? And this is the qubit 0 is the vector 1, 0, and the qubit 1 is the vector 0, 1. But we can use any orthonormal vectors, okay? How we can formalize this the quantum superposition? So a qubit is in superposition. So this means that it is a vector in C2, and this vector so can be written as alpha 0 qubit 0 plus alpha 1 qubit 1. And here we are saying that we have a superposition at the same time in qubit 0 and qubit 1. This is for 1 qubit. After that, we can construct 2 qubit basis state, and the operation we will use is the transfer product. As you can see here, for example, the qubit 1, 0, in the 2 qubit case, okay, is the transfer product between the qubit 1 and the qubit 0, okay, and so on. So in a general n qubit state, it is a vector such that it can be written like the sum for x in 0, 1 to the power of n of alpha x, okay, and the alpha x is about the superposition. The superposition is in the quantum world. Classically, we cannot see the superposition. So classically, we cannot see the two that we have a qubit in superposition. We see only bit. There is an operation which allows to transform, in some sense, we can go from the quantum world to the classical world, which is the measurement. Okay, and the measurement also gives us a probability of observation of a qubit. So when you measure the state psi, this gives you a state x, a basis state, with probability equal to the module of alpha x square. Okay, so for example, let me consider this qubit superposition. In simple case, it is equal that this qubit is equal to alpha 0 qubit 0 plus alpha 1 qubit 1. In classical world, we see only 0 or 1. So if we do the measurement operation, we will see the qubit 0 or the bit 0 in this case with a probability equal to the module of alpha 0 square, and we will see the bit 1 with the probability module to alpha 1 square. This is why the sum of the alpha is called amplitude. So the sum of the module of the amplitude squared should be equal to 1 because it is related to probability. Okay, so this is the notion of quantum bit. There is also a notion of quantum operation, and all the quantum operation in this case are based on unitary matrices. So if we would like to transform a qubit to another qubit, we need to apply a unitary matrix. Where a widely known matrix is the Hadamard gate. It's written like this, and so this is the qubit 0. I would like to transform it. I applied my matrix to the qubit 0 and obtain this matrix in a superposition. And this is a state which is called a state in equi-superposition, in the sense that, as you can see, we have the same amplitude. That means that the probability after a measurement, the probability to observe 0 is equal to the probability to observe 1 is equal to 1 over 2. Okay? So to summarize quickly, for quantum computation, so there is the analog of bits are quantum bits. The analog of gates and or not, you use unitary quantum matrices, also call it unitary quantum gate. And after that, when we would like to read the result, we have to do a measurement to find the final state. Okay? Okay, I have to go a little bit faster, but yeah, after if you have questions, so we can discuss more about this part. So this is just to illustrate the idea of Grover search, because here we would like to use this algorithm to design a new quantum perception algorithm. So Grover search, as I said before, is for searching a number in a list. So classical algorithm is a simple algorithm, as you can see here. So we have a loop, and we have to check each element if it is the element we would like we are searching for. Okay, and so the complexity is linear with n. So this is the Grover search. The Grover search, now we use quantum superposition. So at the beginning we have an initialization, and the initialization is the equi-superposition of all the elements of my list. So equi-superposition, in some sense, if we apply the measurement, we will observe each one of the proposition with the same probability. Okay. After that, Grover provided Grover iteration is an operator, unitary matrix operator, okay, so that we can apply it to this state, equi-superposition state or uniform superposition state. We apply this Grover operation square root of n times, and after that, so we will obtain a modified state. We do a measurement. We observe with high probability the element we would like to find. So here to be more precise, when we say that the computational here, so the computational is square root of n, because we repeat this operation square root of n times. Okay, so this is the number of times we will call the oracle. I didn't enter the details, but in the Grover operator, there is an operator which is the oracle, and here the complexity computed with a number of calls to the oracle. Okay. But now the question how to apply this to the perception algorithm. So widely known algorithm, simple algorithm, the basis of neural network. So the perception is works as follows. So we have data. After that is iterative algorithm. Each time we receive a new, so we initialize your hyperplane, okay, your solution. After that, each time you receive a new data point, we will verify if your hyperplane classify well this data or not. If not, there is a mistake, so we do a kind of update, and you update. Okay. So the computation, two well-known results is the computational complexity, which is linear over n. So we have to do a loop and check that all the data points are well classified. This is why linear over n. And we have the result known by Novikov bound about the statistical guarantee that say that the number of iteration is bounded by 1 over gamma square. What is gamma? Gamma is the margin of your problem. So this is the distance between your hyperplane and the data points, which is the nearest of the data points, the nearest data points in your data set. Okay. So if the margin is small, the task is more difficult. Okay, because the two classes are near to each other. Okay, and so in this case, the statistical efficiency 1 over gamma is more complicated. However, if the data points for the two classes are far from each other, so the problem to find the hyperplane is easier, and so the statistical efficiency is better in this case. Okay. Now I would like to show how we can use Groover to have a quantum perception. The first idea, which was proposed by a paper of Weeby and co-authors, it is a NeurIPS paper. If I remember well, it was published in 2016. Okay, and the idea is the following. Here the classical algorithm. As you can see, here we are looking, trying to see if the new data point is well classified or not. So in some sense, this task is similar to the task of searching for wrongly classified data point. Okay, and so it is a task of search. We can apply, in this case, a Groover search algorithm. And we obtain, in this case, the following algorithm, which is called online. It is not online, but since it is the extension, direct extension of the online algorithm, this is why it is called online quantum perception. So we have the data points here. We initialize our W. This is the hyperplane, okay? And after that, we search for a data point which is misclassified by our hyperplane. If we find a data point which is misclassified, this means that our hyperplane is not a good one. In this case, we do the update, and so on. Here, so since we are using the Groover search over the data points, so the complexity, instead of having linear complexity with the data point ends, we will have a square root complexity. This is the advantage of using Groover search. However, we don't have any gain about the statistical efficiency. This means that the number of iteration is bounded, like in the classical setting, by 1 over big O for 1 over gamma square. Okay. So now the question: can we have a quantum algorithm such that we can improve this statistical guarantee? Yeah.
Additional space is required for Groover's algorithms.
What do you mean by additional space?
Ordinarily, the space for storing and integers is required.
Okay,
order
okay.
and so.
Okay, yeah, but what? Maybe I didn't precise this. So here in all this part, I will not enter in the detail about how to conceive, in some sense, the Groover algorithm. Here I suppose that we have the Groover search algorithm, okay, and if we have it, how to apply it to the problem of classification when using the quantum algorithm. It is true that after that, if we would like, even in the standard case of search, if we would like to compute the real complexity of the algorithm, maybe we have other complexity to be added to the square root of n, that the complexity of having the oracle and so on. But here I consider that I have the Grover algorithm, which is working, and I compute the complexity over the number with respect to the number of calls of the oracle. Okay, so I didn't include if we add another space to be able to implement it. Since this is related to implementation of the Grover search algorithm.
Oh, okay. Thank you.
Any other question? Okay. Okay, so yeah, I will go fast now, and I will conclude, and after that we can discuss if you have question. Just to show you quickly before concluding, another way to do the perception, which is called the version space perception. What is the version space? It's the space containing all the solution of our problem. Okay. If we would like to solve the perception problem, because the perception is just finding one hyperplane, one idea is to generate many hyperplanes. Okay, and this in having this many hyperplanes, the question now is to find one hyperplanes in the version space. This means that one of these hyperplanes can well classify the data. Okay, and so now we transform a problem on a search problem on the hyperplanes, not on the data points. And we obtain this kind of algorithm. So we generate a lot of the hyperplanes, and after that we apply now this quantum search to find one hyperplane that classifies the data. So as you know, in perception, compared to SVM, the solution is unique in SVM, but the perception is not unique. The goal is to find only one hyperplane from all the hyperplanes that can classify the data. Okay? And when we apply this kind of algorithm using a Grover search, the complexity will be the same. However, we can improve the statistical guarantees, the dependency over the margin, from 1 gamma square to 1 square root of gamma. The question now is, can we have the two advantages on the number of examples and advantage on the gamma square? So we can mix the two ideas to design a kind of hybrid quantum perception, such that we generate many hyperplanes, and after that, instead of looking one hyperplane, we are looking for one data point which is misclassified by the hyperplane. Okay, so for each hyperplane, we look for if there is one data point which is misclassified. If we use this strategy, we can show that we have a computational complexity improvement from n to square root of n, and we have also a statistical efficiency of improvement from 1 gamma square to 1 over gamma. Okay, let me conclude by showing some simulation comparing these three quantum perception algorithm with the standard classical algorithm. So this is the version space, this is the online, and this is the hybrid, and this is the number of operations compared to the classical perception. So we applied, this is classical implementation, we applied this on Iris, the dataset, well-known easy task, and we find that the classical algorithm perform better in this case. So the time complexity or the number of operations is less. So for this is in some sense say that if we have easy task, we don't need really a quantum algorithm to solve this task. So the classical algorithm works very well and don't need to try to have a quantum algorithm for that. However, we generated a specific data set which we call it hard. Why hard? Because it is hard for the classical perception. Hard in the sense we know that the number of iteration will be high in this setting. So the way how the data are created allows us to have a number of iteration high when using the classical algorithm. And in this case, we can find some improvement. And when we compare, so the three quantum algorithm improves compared to the classical one. And when we have both improvement over the number of samples of the current statistical guarantee, we have a better improvement in this case. Okay, so To conclude, so I showed you some new models based on quantum-inspired or quantum-enhanced machine learning using concepts like superposition, entanglement, lower-rank decomposition. This also provides a theoretical, well-founded algorithm, and this is promising to have a better quantum machine learning algorithm. So if you would like to know more about our work in this field, we can take a look at our project QuantumL, which is funded by INR, the National Research Agency in France. Thank you.
The next speaker is Dr. Enrico Rinaldi. So the title is Parameter Estimation from Quantum Jump Data Using Neural Networks. Please start.
Thanks, everyone. My name is Enrico Rinaldi. I am a senior scientist at Quantinuum here in Tokyo, and also a visiting scientist at RIKEN. Today, I want to talk about one specific square in the image that the previous speaker has shown you, and in particular, how to use classical machine learning algorithms, but for quantum data. This is one of the possible directions of the so-called quantum machine learning field. Specifically, I have a task in mind that is the task of parameter estimation. And I want to apply this task to a quantum system. And in particular, I will talk about open quantum systems. So let me briefly go through these keywords here. So you're probably familiar with parameter estimations. The task is to estimate or find unknown parameters of a model. In this case, the model that we have in mind is the physical Hamiltonian of a quantum system. So I want to be able to extract information about the parameters of a quantum Hamiltonian in a system that I'm using as a sensor to sense the environment. And in particular, I want to use the properties of quantum mechanics to enhance this sensitivity to the environment. This is a task that is routinely done in the field of quantum metrology, where people use quantum systems that let you go beyond the limits of what is possible to do with classical measurements. And one example is detecting gravitational waves, for example, at the LIGO experiment. Another example is the task of measuring a magnetic field using a quantum system. And this is much more precise than any other way we have of measuring magnetic fields. This is useful for navigation, geology, and so on. So the task, again, is parameter estimation for a quantum sensor that we describe as an open quantum system. Quantum system connected to the environment and monitored from the outside. So the question we ask here with this introduction is, can we use machine learning or deep learning in particular to improve the task of parameter estimation specifically for this type of systems? And the answer is yes. And we recently published our study of benchmarking our deep learning method in the Journal of Quantum Science and Technology. So let me give you an introduction about the quantum system that I am considering, because this might be new to most of you. The model of an open quantum sensor, in just a few pictures, is that we take a quantum system, here represented by a qubit, and we know that this qubit is interacting with an environment that we want to measure. And this is an external field that has a specific value of amplitude and a specific coupling to this qubit. Then we observe this open quantum system, for example, by using a photodetector, and we look at the photons that this quantum sensor is emitting as the qubit and the external field interact with each other. So this type of setup is a continuously monitored open quantum system. And what we are actually observing from outside in our detector are single photons that hit our detector and give us a timestamp. So we can very accurately measure the time interval between two consecutive single photons hitting the detector. And from this type of data, which is classical, it's in your device, but it's actually including quantum information because it comes from a quantum system, we want to estimate the parameters of the sensor. So the question here is, given this setup, can we precisely and robustly extract the value of the system parameters, this one here? Okay, of course, there are many ways of doing this, and people have been doing this in the past few years since developing the technology for these quantum sensors. And the best way people know how to do this is with Bayesian statistics. So I'm going to also describe briefly what the Bayesian estimation process is, but I want to compare it to our new method, which is based on deep neural networks. And here I'm giving an overview of the different ingredients of the two separate methods. So on the left, the Bayesian estimation method is what we take as our benchmark. It's the best known way of extracting these parameters. Given a data set, which is a list of time intervals from your detector, Bayesian estimation will give you a posterior over the parameters, here represented by a two-dimensional space of parameters theta 1 and theta 2. For the machine learning case, the data is again the same list of time intervals from the detector, and this type of data is fed into a different type of neural networks. And the output of these neural networks is now a point estimate for the parameters of the model. In this case, again, a two-dimensional parameter space. In my talk, I will not describe a third possibility, which is now combining Bayesian statistics with deep learning, Bayesian deep learning. I will only take Bayesian estimation as my baseline and then compare a machine learning method to Bayesian estimation. But moving forward, one can also study an approach based on Bayesian deep learning. Now, our machine learning based approach, of course, is based on data, and we consider both classical data, where quantum information is not available, and quantum data, where quantum information is available. And then we took both these approaches of estimating the parameters and we compare them with each other. So what is the difference in this context between classical data and quantum data? So as I said, we are observing photons coming out of a quantum system, okay? If we have a good detector, we can really get the information about the quantum process going on. But if our detector is not very good, and specifically we do not have enough resolution in time to detect single photons, what we will be detecting is just a collection of photons. We don't know how many, but we know some intensity that they produce inside our detector. And that is a collective data that is representing the total sum of these time intervals that we don't have enough resolution to detect, and therefore we just average over. So this is some sort of smoothing averaging over the different time intervals. And since we cannot get the correlations between the individual time intervals, we do not have access to the quantum information for this system. So what we get instead is, as a function of the parameter of the system, in this case delta, we will get some value of the intensity of the photons hitting the detector. And we see that from this curve, for each parameter, we expect on average to see a specific value of this intensity of photons. The situation is much more complex when we have access to the single photon counts and we have access to the correlations between different times when the photons hit the detector. So here again, for the same value of the parameter of the system, delta, you can see that there are different distributions of these time intervals between photons. And the situation on the right is richer in terms of information than the situation on the left. And this quantum data, this is what I call a quantum data, is going to help us when we do the parameter estimation task, because we will be able to access more information about the system. A different view of the same process is when we take a view of the histograms or the frequency of these time intervals. Again, for the classical data, we do not have access to the individual time intervals. So what we observe is just an histogram over the possible intensity of the photons hitting the detector. Here for a specific value of the system parameters. On the other hand, if we have access to single clicks, we can see a much more interesting distribution. Again, for the same value of the internal parameters. Okay, given this data, the ability to have quantum data through single photon resolution in the detector, we want to use Bayesian parameter estimation to find out what are the parameters of a system given a certain observation of time intervals. So for this, we're going to use Bayes' theorem, and we're going to evaluate the posterior over the parameters using Bayes' rule. Brief summary for those of you who forgot Bayesian statistics. What we want to get is the posterior over the parameters, so a probability distribution over the parameters of the system given a specific value of my data string in this case. And the ingredients that I need for applying Bayes' rule are a likelihood, which is in the numerator, a prior, which I can set to be constant if that's what I need, and the evidence or the marginal likelihood, which is an integral over all possible values of the parameters. This process looks more or less like this in a picture. We start from data, and the data for us are going to be these time intervals, tau 1, tau 2, and tau 3. Given this sequence of time intervals, my posterior is going to look like, in this case, a probability distribution over the parameter delta. And here I'm using the blue color to represent the probability distribution. You see a darker color, it means a higher probability, and white color means a low probability. As I get more information about these time intervals, my probability distribution over the parameter delta is becoming more and more concentrated, and the region of high probability, you can see here, if I collect enough data, is around the true value that I know about the system. So this is just a test. I generated data given a certain parameter, so I know the ground truth, and then I apply the Bayesian statistic framework, and I get a posterior that is concentrated around that ground truth value, given my generated time series of intervals. Okay, this is an example where I'm just doing this for one parameter. Bayesian approaches become more expensive, and so this is one of the challenges in Bayesian parameter estimation, is that first of all, I need a likelihood, so I need to be able to compute what the likelihood is. And for this, when it comes to a quantum system, I need to be able to model my quantum system accurately in order to get the likelihood. This is often not possible. And this probability distribution of my data depends on what I know about the system. So this is sometimes not practical in real world. Another ingredient of this Bayesian framework is the normalization factor, the evidence. And in this case, it could be computationally expensive to get this value accurately, in particular when the problem is high dimensional. We resort to Markov chain Monte Carlo methods that can be very expensive. And this is also why sometimes using this method in real world settings where you want to deploy these quantum sensors in very specific environments where you don't have a lot of computational power available can be challenging. So given this baseline, I want to show you what we did with deep neural network. And using deep neural network, we tried to address those two challenges in the previous slide. How do we get around knowing the exact likelihood, and also how do we get around the expensive part of computing the evidence? In this case, we are using a neural network to output an estimate of the parameters. So in this case, we don't have the full posterior distribution as the output. We're just getting a point, one number or one vector, depending on how big the parameter space is. So we take this quantum data and we take it in two different forms to fit it into two different types of deep learning architectures. So this string of time intervals, you can see it as a sequence and use it as input in a recurrent neural network type architecture. Or you can take this and average or histogram over a certain number of bins, which is a hyperparameter that we can fix to some number, in this case, for example, 400. And then we can use this as a vector of counts or frequencies and use it as input to a fully connected neural network, where the input dimension doesn't change. The output of these neural networks is going to be of the same kind, and it's going to be the parameter vector. In the case of a two-dimensional problem, my output is going to be two neurons outputting the value of the first parameter in the first neuron and the second parameter in the second neuron. We did all this using TensorFlow, and all the code and data are available for reproducibility on GitHub and Zenodo. Okay, so I said that we're using deep learning, so we need to train these neural networks. For training, in this specific case, we work under the assumption that we build the data set, so we know what's going on, and we can really benchmark the methodology, okay? So we simulate these trajectories, these sequences of time intervals using software developed for studying open quantum systems called QTIP. We generate about 4 million trajectories. We do it for the case where we are only estimating one parameter. So there is only one free parameter in the Hamiltonian of these quantum systems. And we also do it for the case when we have two free parameters in the Hamiltonian of the system. Then we train the neural networks in a supervised way, where we know the input trajectory and we know which parameter value generated that input trajectory. So in this case, we do have ground truth because we have been generating this data ourselves. But the test that we do is on data that the neural network hasn't seen. Of course, we have about 10,000 trajectories that were not included in the training data. And these are both with one parameter and with two parameters as output. Okay, these models that we're using are rather small. So after training, they really take up a few kilobytes of memory, so they can be deployed on edge devices and on any quantum lab or wherever a quantum sensor is needed. So they're very efficient from this point of view. So of course you have to spend some time training these models before you can put them out there and use them for inference. But at inference time, they will be much faster than any Bayesian framework. Now, this is obviously good as long as the performance of this method is similar or better than the one that we get from Bayesian parameter estimation. So let me show you what is the comparison between our baseline and our method. So here I'm showing on the y-axis the mean squared error of my predictions. So remember, we know what the ground truth is for this one parameter. And this one parameter, the true value of this one parameter delta, is on the x-axis. Okay, so here I'm showing two lines, connecting points. So the points are in red for the case where we use classical data. So here we have no information about the quantum correlations between single photons. And our predictions can achieve a mean squared error that is of the order of about 10 to the minus 1 or slightly lower. Okay, so in the Bayesian case, without access to quantum data, I get this type of mean squared error for this baseline. If I use quantum data, on the other hand, I can get much lower mean squared errors, usually a factor of 2 or more. In particular, there are features in this quantum data that depend on the parameter of the system. You can see here, for example, when the parameter delta has a certain value, the power of the quantum data allows us to get a much more accurate prediction for the parameter. Now, for these two cases, we use the exact same test trajectories, and so this is a fair comparison. And here is what happens when we use our trained neural networks for the same test trajectories. Both the RNN type neural network and the fully connected neural network can achieve a similar value of the mean squared error as our baseline, the full Bayesian framework, which is down here in yellow. And you can see that since we are using the same quantum data, again, we can recover those features that are in the quantum data that depend on the true parameters of the system. So here, for one parameter, we are demonstrating that we can get as good estimations of the parameter as the Bayesian statistical analysis. This is a case where we're trying to estimate two parameters at the same time. On the left is the full posterior from Bayesian inference, and on the right is our neural network inference. And again, we can see that for the mean squared error, these are more or less similar. A better comparison is probably this one here, where we we compare again our baseline model with our neural network model. So for this two-dimensional case, at inference time, so on the test set, we can obtain results 10,000 times faster than by performing the full Bayesian statistical parameter estimation. So this is advantageous, and it becomes even more advantageous for higher dimensional problems. Now, here you might ask yourself, well, if you do this with simulated data and you know the ground truth, how are you going to do it in real life where there is no ground truth? Is it possible to get some ground truth, or how is the training going to actually behave when you are in a more realistic setting? For example, you have a quantum sensor, you're in a quantum lab, and you are trying to estimate these parameters from a lab apparatus. Okay, so we ask ourselves these questions, and in particular, we want to understand if having access to noisy data, so data that comes from an actual real-world setting, instead of being simulated, affects our results, and how it affects our results. Now, we consider two types of noise that can affect our results, and this type of noise is typical in any realistic setting. One noise is that our measurement device is not very accurate at estimating the time intervals. And in fact, the time intervals have some jitter. They oscillate. They're not precisely measured, but they can be a little shorter or a little longer. We call this the jitter noise. The other type of noise is related to the question of having access to real ground truth data. So we ask ourselves, what if the true parameters, what we think are the true parameters, are actually not the true parameters, and they have been miscalibrated, or they have a certain error that we don't know about. So this is a more realistic case where your training data comes from the device, you're not simulating it yourself, and when it comes from the device, you think you more or less know what's going on, but there might be something systematic that you don't understand. So for the first type of noise, you can imagine that we now have a trajectory of photons that we measure, and the time intervals, instead of just being what we had before, have been shifted a little bit. And the shift of each time interval is represented by adding a Gaussian random variable with a specific variance. So the performance of our method and of the baseline Bayesian method in this context is represented by this plot. So here we are fixing one specific parameter for the system. So we are looking at one system, and we test our trained model for different values of the variance in the noise. As you increase the noise here, the Bayesian inference is giving you a prediction that is farther and farther away from the true value of the parameter. So here the true value is the 0.27, and the mean squared error of the predictions for the Bayesian method are pretty good when there is no noise, and as the noise increases, they become very bad. So the parameters you're estimating now in the Bayesian case, when there is a lot of noise, are going to be wrong. This is because the noise is not included in the likelihood that you're using in your Bayesian method. So if you are not modeling the noise, because you don't know that there is noise, or you don't know the sources of your noise, then the Bayesian method will obviously fail. This is well known. Now, the larger the noise, the larger this mismodeling that you have in the Bayesian method. the neural networks do not suffer from this problem, mainly for one reason, because they've been trained on enough data that they understand that this jittering can be corrected. So if the neural network has had enough data to train on, it has built internally a representation of the process and can handle specific levels of noise. This would fail at some point, of course, this is not magic, if the data is not enough, for example, for the neural network to overcorrect for this jittery noise. So here is an example of the difference between training a neural network on data without knowing what the likelihood is and relying on a statistical method that requires you to model the system and to understand how the system works, which is the Bayesian method. The second type of error that we considered is when the true value of the parameters is not the correct value, but it has been shifted for some reasons unknown to us. And this is equivalent to adding, during the training phase, some noise to your labels. So as I said, we are using a supervised learning framework. So we have input and output data. And what we do to test this type of noise is we modify the labels by adding some random noise, again, with a certain variance or strength. Here is the plot representing the results. It's a little bit complicated to explain, so let me go through it step by step. Again, we fix our parameter delta, 0.27, but at training time, this 0.27 has been changed. It's not 0.27, it's 0.28, 0.277, 0.262. It has a certain variance. Since it has a variance, and we put it in, we know that we expect this training to have a specific mean squared error because we manually put in this error to represent our uncertainty on the labels. So we would expect from the training data to get something like this dashed line. Okay, this dashed line is just the prediction that we expect from training with a specific variance in our labels. The red result is the ideal result that we would get if we didn't have any noise and if we were using the full Bayesian framework. Since we know that this data is wrong, we know that there is going to be this intrinsic mean squared error in our training data. And this is what we expect with this dashed line. But the neural network is actually insensitive to this problem in the data. Again, if the variance in the training labels is not too big, let's say up to 0.4 for the variance sigma squared, we get from the neural network the same result that we would get from the ideal Bayesian framework analysis of the data. So you can see this as some robustness of the framework to the noise that is included in the training. Again, this is not magic. It's due to the fact that if you have enough data, the neural network can learn that there is a certain shift in the labels and can correct for it up to a certain amount. So as you can see, if I have too big of a variation in the labels, my predictions will start to become poorer and poorer. And this can probably be ameliorated by including more data in the training. Now, what I've shown right now is that we can do pretty robust parameter estimation with neural networks. I've shown that the results that we get from neural networks have the same performance as the full Bayesian estimation process in the ideal case, but they are much faster. So some of the advantages of this method is that they do not require a likelihood. So we do not require to model the quantum sensors that we want to deploy. We also do not really need big data because these models are rather small with a few thousand of parameters. So something around 10,000 or 100,000 trajectories are enough for us to train the parameters very accurately. And we can deploy this type of neural network models on edge devices. So we can make them available to scientists in quantum labs or where quantum sensors are deployed. And in our work, we have released all the code and data following the practice of reproducibility. So before I conclude, what are the prospects for this type of techniques? Now, there is a very interesting and important task in quantum metrology called quantum imaging. Quantum imaging is using single photon light sources, either from organic materials or from inorganic materials that have been treated, to improve the features that we can access with microscopy. So in other words, we're using the features of quantum mechanics to improve upon our limitations of visualizing very small structures in materials or in organic elements. At the moment, the data analysis part that is required to utilize the data coming from these quantum microscopy labs is very complicated and expensive. And we want to deploy this type of neural network techniques for this type of quantum imaging problems in order to not only improve upon the previous methods, but also make them faster and available to more people. Thank you very much.
The final speaker is Dr. Hayata Yamasaki, and the title is Advantage of Quantum Machine Learning from General Computational Advantages. So please start.
Thank you for introduction. I am Hayata Yamasaki, working as an assistant professor in the University of Tokyo. Today I would like to talk about our recent progress on advantage of quantum machine learning from general computational advantage of quantum computation. I start with talking about background. So quantum machine learning is an emerging field of research that uses quantum computation for machine learning. In our IT society, data processing in our daily life is supported by machine learning technologies working behind it. Quantum machine learning is an emergent field of research that aims at further speed up and scale up of these machine learning technologies by using the power of quantum computation. One of the big future milestone of quantum machine learning will be demonstration of provable advantage of quantum machine learning over any classical learning methods in solving some conventional learning tasks. So in today's at the moment, under current technology, quantum computation quantum computers might not be powerful enough to implement such powerful quantum machine learning methods, but the main topic of this talk is for which task we can prove the advantage of quantum machine learning and what kind of task we should demonstrate in the future. So before going into detail, I would like to briefly introduce what I am doing from the broader perspective. In a series of my work, I am trying to connect recent advance of quantum technology in experiment and our future advance of our IT society based on these quantum technologies. To do that, to achieve this goal, I am working on several different topics that I think that in my mind is connected to each other. On the application side, I am developing useful quantum algorithms that especially aims to accelerate machine learning tasks with high speed and applicability. And also, to realize such useful quantum algorithms in actual quantum experiment, it is indispensable to suppress the effect of errors. In the experiment, we inevitably have noise in quantum devices that will randomize the output of quantum computation. So we need a technique to suppress the effect of error, which is called fault-tolerant quantum computation. And I am developing protocols that are to realize low overhead scalable fault-tolerant quantum computation. On the more physics side, I am developing analytical techniques to investigate efficient quantum operations, to quantitatively analyze how to use quantum property as a resource for quantum computation and quantum information processing. On each of these topics, I have several works. So today I would like to talk about our recent analysis on the provable quantum advantage in solving learning tasks. And in the meanwhile, in the next slide, I would like to briefly explain other directions of my research for developing quantum algorithm for finding optimized features. The feature of this algorithm is that this achieves exponential speed up compared to the state-of-the-art classical algorithm for solving the same task. And this does not use the super-sum low-rank matrices. So without these assumptions, this has a wider applicability than other quantum algorithms achieving similar speed up. So another direction, I would like to also mention another directions of my research briefly. If you are interested, we can also discuss this. So for the FTQC, a series of my work develops a time-efficient constant space overhead fault-tolerant quantum computation. And also I am working on several different aspects of quantum error correcting codes. And also for the efficient quantum operations, I am developing efficient protocols for property testing for quantum states. And also I am working on so-called quantum resource theories, that is a theory to quantitatively analyze the quantum properties as a resource for quantum computation. So before going into detail on the provable quantum advantage, I would like to briefly explain what I'm doing on the algorithm side. In a series of our recent findings, we showed that quantum machine learning can achieve the following task exponentially faster than the corresponding classical state-of-the-art algorithms. The task here is to find the important features from exponentially large parameter space for learning classical data. I would like to explain one example of such a task. So in one of our work, we consider learning using a model of shallow neural network, which is a 3-layer shallow neural network, and we can show that any function with d-dimensional input can be represented as a shallow yet wide neural network where the hidden layer can be exponentially large in terms of data dimension d. But at the same time, recent research on the so-called lottery ticket hypothesis showed empirically observes that within such a large-scale neural network, it is often the case that we only have a very small number of nodes that has large weights, and very small number of nodes, only indeed a very small number of nodes is relevant for learning. So based on such a observation, we consider setting of learning functions that is represented as an exponentially large neural network, but indeed only a polynomial number of nodes in the hidden layer has large weights, so that only polynomial number of nodes should be relevant for learning. We consider learning of such a function, and then the task here is within the exponentially large neural network. How can we find the polynomial number of high-weight nodes that is relevant for learning? So we consider this task, and in the context of lottery ticket hypothesis, there are several classical algorithms for this kind of searching available. But conventionally, but usually such a classical algorithm basically represents such a large-scale neural network as a bit string. We need to store this and then perform training or searching for using such a large-scale neural network. So since such a classical algorithm stores big neural network as a bit string, this inevitably requires exponential runtime in our setting. By contrast, we develop quantum algorithms that does not store such a large neural network as a bit string. But from the data, our quantum algorithm directly prepare quantum states whose probability amplitude represents the weights of the nodes in the hidden layers. And by preparing such a quantum state and by just measuring such a state, we can sample high weight nodes with a high probability. Then by repeating such a sampling, we can collect a set of important nodes by using quantum algorithm. It turns out that this quantum algorithm runs within the linear runtime in terms of data dimension d. So this achieves an exponential speedup compared to the corresponding classical state-of-the-art algorithms. And we are developing such a in this way we are developing quantum algorithms in a reasonable classical setting of classical machine learning to achieve how we can use exponential speedup of quantum computation in such a reasonable setting. So this is in our opinion, this is one way to achieve end-to-end speedup in a reasonable conventional machine learning tasks by using quantum machine learning. But the problem here, the motivating fact for the rest of our talk is that it is not yet proven from this work that our quantum algorithm outperforms all possible classical methods. So this only achieves the exponential speedup compared to the existing classical method. So for the learning task, if someone come up with some new classical algorithm that solves this task in a very clever way, there might be this speedup may be cancelled by the progress on the classical side. So this possibility is not ruled out. So while this task we think is useful, but so this is a drawback of this kind of work. So it's hard to prove that this kind of quantum algorithm outperforms all classical methods in such a practically useful setting. So the difficulty here is the difficulty here arises from the difference between computation and learning. So quantum computation is advantageous compared to the classical computation in solving computational tasks, but it's not immediately clear whether it is advantageous in learning tasks, since these are different tasks. So computation is a task of evaluating some known function. For example, you have a given input, and then we know what function is, and then computation is just compute this function and then output it. For example, there's a well-known quantum algorithm called Shor's algorithm. This computes a function of discrete log, for example, or factorized integers. And so classically, it is unknown how to compute discrete log within polynomial time, but the quantum algorithm can compute discrete log function within a polynomial time. However, learning is a bit different task. Learning is a different task. Learning in the learning setting, we don't know what the function is. We have a polynomial number of input-output relations as an example. Then but we never know the true function is. So from the data, we compute hypothesis, that is some estimation of the true function. And then for the future data, for the future input, we basically applied such a hypothesis to predict the corresponding output. And the question, these tasks are quite different. And while quantum computation is advantageous over classical computation in solving computation tasks, the problem here is how to bridge connection between computation and learning. So in today's talk, I would like to connect these, discuss this, how to address this point, this difference. So there are several works on such a connection between computation and learning. But in the previous works, advantage of quantum machine learning is shown only by using the computational advantage of Shor's algorithms. By contrast, in our work, we prove advantage of quantum machine learning from general computational advantage of quantum computation. Our main theorem is as follows. For any quantumly advantageous function of n-bit input, so quantum advantage function is that some function, okay, I will explain that, the detail will be explained later, but for any function that is computable within polynomial time by quantum algorithm, but not computable within polynomial time by classical algorithm. And here, such poly means that this is even impossible to compute, even with the assistance of polynomial size data, or in the technical term, this is called advice string. But even with data, this is impossible to compute by classical computation. Then, for any such quantum advantageous function, we can construct a corresponding supervised learning task with classical data that is such that some polynomial time quantum algorithm can achieve this learning. We construct such a quantum algorithm. But at the same time, we can prove that no polynomial time classical algorithm can learn to make prediction for this task. Basically, we cannot learn and make a prediction for this learning task as long as we use classical computation. So, yeah, what we have shown is that in principle, if we can learn, suppose we can learn and make prediction for this task, we can compute the computational hard function classically. So this is basically impossible. So we have proven this. So that compared to in the previous work, we only need such a function is limited to functions very limited to a special class of functions such as discrete log or factoring. By contrast, our contribution is that we opened a new opportunity of demonstrating advantage of quantum machine learning using any quantumly advantageous function, not even beyond Shor's algorithms. I will explain the examples of such function in the last part of this talk. So I'd like to explain more about the setting of, clarify more about the setting of our learning tasks. So in principle, to show such an advantage, computational advantage to show such a computational advantage of learning, we need to work on some conventional setting in the computational learning theory. So in the computational learning theory, there's a conventional model called PAC learning model, which is probabilistically approximately correct learning model, or PAC model for short. So this is this task is basically captures the concept of supervised learning, essentially classification. The task is as follows. So we have a set of functions to be learned. So this is called concept class. It's a class of functions. This is a set of functions. So we don't know which parameter S is. So S is a parameter to represent a true function to be learned. But we have for the given input, this concept outputs some class. The output of this function is its output for the binary classification. So for each x, the concept classifies inputs into category 0 or category 1. So we have a polynomial number of input-output pairs from some unknown distribution, which is a true distribution. Then from given samples, we perform quantum or classical computation to output some prediction, which is also called hypothesis. Hypothesis is the estimation of the function to be learned, estimation of the concept class. So the only requirement is it's not required that this C is exactly predicted, but the requirement here is that for the new given input, we evaluate our hypothesis efficiently using the predicted hypothesis, so that this new prediction is correct. The new prediction coincides with that of C with high probability. The condition for the feasibility of learning is efficient learnability and efficient evaluability. So this learning is learning our hypothesis C prime should be efficient, and this C prime should be efficiently evaluated for the future input data. So efficient here I mean is polynomial time within the input size, which is n bit n. So we require this, and then we need to use this kind of model to analyze the computational complexity of learning. Yes.
What is the difference between C prime and C?
C is a true distribution. C is a true function, true concept, which may be unknown throughout the learning. But the whole point is that for the data, on the support of data distribution, this C prime and C should look the same.
In some sense, C is the true concept,
yes,
and C prime is the one which will be found by the learning process.
Exactly. Yeah, it's just a prediction. Yeah,
okay. Thank you.
Yeah, it should coincide only on the support of data distribution. Yeah. So that's a setting. So, but this is a general setting. We consider more specific setting motivated by what is going on in the actual machine learning. So we consider setting motivated by feature mapping and linear separation. So we consider that given samples are in the packed learning, given input-output pairs of samples are given according to some data distribution with some unknown concept C with parameterized by unknown parameter S. But the task here is to find S such that the task here is to find such an unknown parameter representing the true concept. But we consider a setting where this concept is given in the form of linear separation. So here's a setting. So we have an input data comes from a space of d-dimensional. Input space is n-dimensional space, and then we apply feature map. So some map to map input n-dimensional data into some feature space. Then so that some hyperplane on the feature space can classify the data. So this is maybe a conventional setting of linear separation, but if we just take Euclid vector space as a feature space, it's in principle hard to, it's very challenging to prove the advantage of quantum computation over classical computation. The trick here is that we took, for the feasibility of analysis, we took this vector space. We took as a feature space the vector space over a finite field representing bits, and now this inner product representing hyperproduct is a bitwise inner product, which is essentially the inner product over this vector space. So it's a bitwise inner product. So in this way, we formulate our concept class based on the conventional learning method motivated by feature mapping and linear separation. But the trick here is that we use a vector space of finite fields as a feature space to say something non-trivial in the analysis. Then, as a feature map, we took what we call quantumly advantageous function. The feature map used for concept class is in the terms of computational complexity theory. It is represented as this. So this means that this part means that this is the function should be computed by quantum computation, but not in this space, representing that it should not be computed by classical computation, even with assistance of data. So this part means that this is conventionally BQP means a class of functions with single bit output that can be efficiently computed by quantum computation. So FBQP means that it may be a function with outputting multiple bits. So it's really not a single bit function, but multiple bit functions. So here we consider a heuristic class, which means that it should be quantum computation can compute such a function on the large fraction of inputs, but not on the whole, not in the worst case. So so roughly speaking, on average, quantum computation can compute such a function. So this is called a heuristic complexity class in the computational complexity theory. So we need to take such a heuristic complexity class to analyze the probabilistic task of learning. So quantum advantage function should be quantumly computable within for the large fraction of inputs, but classically it should not be computable classically for the large fraction of inputs, even with some advice string. So this advice string means that this advice string is any polynomial length bit string to accelerate computation. For example, this is a given classical data or hyperparameters or some learned parameters of the model that potentially accelerate learning. So even with such data or some parameters for neural network, for example, we should not be able to compute such features. So we take such a function as a feature map in our setting. So but the whole point is that in the previous work, previous work was limited to using a special class of such function, such as discrete log computed by Shor's algorithms. But in our work, we can take any quantum advantage function for our quantum machine learning algorithms. So using this setting, motivated by linear feature mapping and linear separation, our main result is as follows. So for any target distribution, for any data distribution, and any quantumly advantage function that can be computed quantumly but not classically, we consider the concept class, which basically maps input space into input and dimensional input into feature space representing space of bits, and then consider hyperplane on the feature space for the classification. For this task is quantumly efficiently learnable and evaluatable because we can construct a polynomial time quantum algorithm to achieve this learning. But at the same time, we can prove that this is not classically efficiently learnable by any classically efficiently evaluatable hypothesis class. So we can show that we cannot learn and efficiently evaluate any hypothesis to achieve this learning. So technically speaking, what we can show is that if we can learn or efficiently evaluate hypothesis class to achieve this task, then we can basically compute this function. So this is but this is impossible. So this is what we can say in our setting. So in the rest of this talk, I would like to briefly discuss how we can argue this kind of theorem. But before going into detail, I would like to briefly mention what's the implication for the learning in general. So you might be thinking that this feature map is just a contemporary advantage function such as discrete logs, so it's a bit artificial compared to the conventional learning setting that we are using in our everyday life. But we need to recall that even in the classical machine learning, we are not really using a natural function, but even in the classical machine learning, what we are using is often a very artificial functions. For example, to classify input image, for example, we are in many cases we are just using artificial neural network, which is often not, which is basically motivated by, like, for example, neurons in brain and so on originally, and so it's not necessarily a natural function to represent such an image, and it's often the case that the output is just performed by linear separation following the designing of feature map artificially. So in view of such a situation, what we can say is that what we can observe is that we can now optimize features over any contemporary advantage functions to get advantage of quantum machine learning. So it's unknown which contemporary advantage function really represents the data in practice, which contemporary advantage function we should use to achieve better performance in practical data. But it was also unknown in the classical case until we really observe the empirical good performance of the artificial neural networks. So our contribution here is that we open the opportunity to use contemporary advantages, a very large class of contemporary advantages functions beyond Shor's algorithms to make sure that we can provably show the advantage in the conventional setting of classifications. So to show such a result, we develop we clarify quantum algorithm, polynomial time quantum algorithm to achieve this learning task. Our learning task is very simple. Our quantum algorithm is very simple. But the difference from conventional learning algorithm is that we work on discrete feature space representing bits. So we can straightforwardly use gradient descent algorithm since the space is now discrete. Instead, what we have shown is that we can, from the input data, we compute features using quantum algorithm by evaluating contemporary advantage functions, and then we need to estimate some unknown parameter representing concepts. But what we have shown is that we can just solve the system of linear equations to estimate such unknown parameters. And then using a solution of the system of using a solution of system of linear equations, we can construct hypotheses by just evaluating hyperplane corresponding to estimated parameters. So technically speaking, although the solution of this system of linear equations may not be exactly correct, may not exactly coincide with true parameter representing true concepts, but what we can show is that the hypothesis constructed in this way is correct for the large fraction of inputs that are given according to some data distribution. So on the support of data distribution, this is correct with hyperability. This we can show. So another difficult part is another challenge for the in the quantum machine learning is how to show classical hardness. Basically, we can show classical hardness for the learning task by contradiction, by contradiction. So what we can show is that if we can evaluate, if we can learn and evaluate some hypothesis for this learning task, we would be able to compute the quantum advantage function classically, which is assumed to be impossible. Without such a computational hardness assumption, basically in the computational complexity theory, it's hard to show anything. For example, like we don't know any proof of P not equal NP, for example. This kind of showing hardness requires some assumption on the computational hardness. So here in our case, the computational hardness assumption is assumption on the classical hardness of computing computational advantageous function. Yes. So the actual logic is as follows. Suppose we have a classical algorithm that can evaluate some hypothesis for our learning task. And also we assume that this is possible for every choice of S. Then we can smartly choose different S so we can choose different S's, and for every choice of S, we should be able to under this assumption, we should be able to have some classical algorithm to correctly classify the data. But for some smart choice of parameters, we can basically reproduce all the elements of the whole values of quantum advantageous functions. So, and this contradicts the fact that this function should be is chosen to be quantumly advantageous function. So this kind of contradiction, by this kind of argument, by contradiction, we can show that no classical methods can achieve this learning task. So compared to the previous work really depended on the fact that this function f is a discrete log or integer factoring implemented by Shor's algorithm. And then the assumption there was to use the assumption there was a hardness of integer factoring or discrete log, and the existing argument really depended on cryptographic argument and assumptions to prove the classical hardness for the learning. But the whole point of our analysis is that our argument does not use cryptographic assumption, but just using a set of parameters. By just choosing a set of parameters, we can prove the classical hardness of our learning task. So as a progress of proof method, this is also new because in a sense that we do not use cryptographic assumptions. So finally, what from our method? What's an example of new learning tasks beyond compared to the previous works? The merit of our quantum machine learning framework is that it is applicable to any quantum algorithm to compute quantumly advantageous functions, which can be beyond the Shor's algorithms. So it is well known that quantum computation can solve integer factoring and discrete log very fast by Shor's algorithm, but the application of quantum computation is not limited to basically quantum is not limited to factoring and discrete log. For example, there are several algorithms in the field of topological data analysis that is in some case we can prove the advantage of quantum algorithm over any classical algorithm, and in some case we can, for example, in the to compute some quantity called Betti number or some other topological invariants, we can show that we can have a very fast quantum algorithm. And also from the number theory, quantum algorithm is known to be able to solve so-called Pell's equation, which is more difficult task than which is considered to be a more difficult task than factoring and discrete log. If we can solve Pell's equation, we can solve discrete log and integer factoring, but it's not known whether, even if we can solve integer factoring or discrete log, whether we can solve Pell's equation. And Pell's equation can be used for other cryptographic tasks than those based on integer factoring. And also, our method is applicable to some functions relevant to BKP complete problems, which are the hardest problem to solve within the for quantum computation. So we have many other examples that is not within the realm, that is beyond the realm of Shor's algorithms. So what's the benefit of this? So it is often said that milestone of Shor's algorithm is to factorize 2048-bit integers. But 2048-bit, so this is used in today's RSA cryptography crypto system. But it's indeed very demanding to realize such a to factorize such a large integers under current technologies. So it will be a milestone of development of quantum computation. But yeah, so basically this is very demanding task. This is only a long-term goal. By contrast, we can use various different computational tasks to demonstrate the advantage of quantum machine learning. So for example, if we can consider a milestone for the harder problem for classical computation, then maybe smaller problem size it can be used to beat any classical method for the corresponding learning tasks. So the open problem will be that so it's still unknown which problem we should use for it to really demonstrate this kind of advantage of quantum machine learning. So it will be an exciting opportunity to seek such a which problem should be to take a look at the concrete problems in more details. In the end, I would like to briefly mention about how to realize this in an experimental setting. So we propose to use a two-party setting where one party is in charge of preparing data, and one party performs our quantum machine learning algorithm to achieve learning. So for example, we use one chip to prepare some classical data, which can be using quantum or classical computation, depending on the choice of feature maps. Then this input-output data should be sent to another party. Then we basically use quantum algorithm or classical algorithm to perform classification to compare their performance. So in this way, we also have a proposal of explicit constructions of a protocol for demonstrating advantage of these quantum machine learning tasks. So in conclusion, computations or learning are, as we discussed, quite different yet closely connected. What we have shown is that advantage of quantum machine learning emerges from general quantum computational advantage even beyond that of Shor's algorithms. And this advantage of quantum machine learning is indeed simply realizable by feature mapping and linear separation, widely used setting in machine learning tasks, whose wide applicability has been empirically known. So thank you for your attention. Thank you very much.